This video clip is part of the EPFL introductory course on information computing and communication. It is the sixth one in a set of video clips on computer architecture. Earlier video clips in this series have shown how computing devices can be built out of transistors and programmed in languages that can be compiled into binary codes executable on such computers. The remaining two clips in this series on computer architecture would explain how computers can be made faster by resorting to different forms of parallelism. The present clip focuses on so-called logic parallelism. Gaining computer performance is of course always desirable, but the architecture plays a key role here. Indeed, if one looks back at the evolution of processor performance, one can see on this slide that it has grown by a little over 50% per year. Yet only about 20 of these 50% are due to transistor having become smaller and faster. The difference between this 20% technology progress and the over 50% real progress is entirely due to smart hardware design. The performance of anything can always be increased in one of two ways, either by reducing the time or delay that it takes to do something, or by increasing the throughput or the number of things done by unit of time. This clip focuses on an example of performance gain through reduction of the time to perform operations thanks to logic parallelism. The next and last clip in the series will then discuss an example of performance gain through increase of throughput thanks to the architectural parallelism. Consider, for instance, how one can reduce the time to perform an addition. In doing so, remember all possible 2-bit additions, observing that if both bits are 1, then the result will include a carry bit into the next order addition. A basic adder starts by adding the two lowest order bits, then proceeds to add the next two lowest order bits. It cannot proceed faster because at every stage it must compute the carry bit before it can compute the next stage. Only then can it move on and on to the highest order bit. Having observed this, building a full adder requires the following. First, computing every result bit requires a bit adding circuit to add the 2 bits of the same order of the 2 operands. Because of the carry, however, for all higher order bits, the bit adding circuits need to be able to add 3 bits rather than just 2. So we need the same circuit at every stage onto the highest order bit, where each of the 3 bits adding circuits is one of those seen in the 4th clip of this series on computer architecture. Such a basic adding circuit thus suffers from a fundamental limitation. The propagation of the carry bit is an intrinsic requirement that prevents computing the addition of all the bits in parallel. The total time required by such an adder is thus directly proportional to the number of bits to be added. Could we possibly do any better? If we imagine that we need to add 2 64-bit numbers, the total time to do this is bounded by the need to compute 63 carry bits. Can we hope to gain anything by splitting the 64-bit number into 2 32-bit numbers and transferring 1 carry bit between the 2 operations? Computing the sum of the 2 lower order 32-bit numbers will certainly take only half the time of what it would take to add the 2 64-bit numbers. However, we cannot start adding the 2 higher order 32-bit numbers until one has the carry bit from the first addition. Thus, one has gained nothing. Now imagine for a second that we invest more transistors in the design, building 2 separate adders for the 2 high-order 32-bit numbers, one that assumes a carry bit of 0 and one that assumes a carry bit of 1. Now we can start adding the low order and higher order 32-bit numbers in parallel, thus taking only half the time. Because indeed, by the time the real carry bit becomes available from the lower order addition, we have the sum of the higher order addition for both cases, carry 0 or carry 1. And what remains to do at that point is to use that carry bit to select which of the two higher order additions is the right one way or the other. So we have essentially cut the total consumption time by half at the cost of investing only 1.5 times as many transistors. One can thus profoundly change the performance of a circuit without changing its functionality. This can be achieved by investing more circuits, thus raising the power consumption, but one could equally well use slower circuits to save power. This is the field of logic synthesis, one of the branches of computer engineering.